Today we're going to talk about a lesson called 8.4, and it's going to have your introduction to logarithm functions. So first, let's talk about logarithmic form versus exponential form. This guy right here is logarithmic form. And then he can be translated to what we call exponential form. And the little b is the same b that's over here. So whatever number is in the base of the logarithm gets put into the base of that exponential problem. What I always tell my kids to realize is you don't have to memorize formulas, you have to memorize process. So when we take a logarithmic expression or equation and change it to an exponential equation, I tell them to say, take the base, raise it to the answer, and set it equal to the number. Now this might not make a lot of sense yet, but if you look over at the logarithm, the base is the base of the logarithm, and that's what we write here. We raise it to the answer, which is over here, and it's going to equal whatever that leftover number is in front of the behind the logarithm. So when I look at number 1, we're going to take this logarithmic expression or equation and change it to an exponential equation. So we take the base, which is x, raise it to the answer, power, which is 5, and set it equal to that leftover number 32. Now you don't have to solve because the directions on this section just said to rewrite into exponential form. Same thing here on number 2. Take the base, which is a 5, raise it to the power of whatever the answer was, 0, and it should equal 1. Now that's a true statement. There's no variable there, and we all know that 5 to the 0 power is equal to 1. Same thing here on number 3. Base of 10, raise it to the power of 1, has to equal 10. Base to the answer equals the number. Number 4, take our base 10, raise it to the negative first power, and it should equal 0.1. Now this is a true statement again, and if you think about it, 10 to the negative 1 power is taking a 10 and flipping it to the base, which makes it a 1/10, and a 1/10 is equivalent to 0.1 as a decimal. Okay, next set of directions say same thing. 1/2 raised to the negative first power equals a 2. Again, negative exponents, take your fraction and flip them around. So the 1/2 would be flipped to a 2, and that would make sense. Now here, they leave a blank, so I'm going to put a variable right there, even though I know there's already a variable in this problem. So we're going to say b to what mystery power, and you know what? Instead of x, I'm going to be really weird, and I'm going to use a question mark. So b to what mystery power is going to give us an answer of 1. Well, if you think about that, the only way you're going to come out to a 1 by raising b to some exponent is if that question mark was a 0. And then let's look at number 7, same thing. I'm going to put a question mark here. So when I rewrite it, b to what mystery power, what do I have to raise it to get back just a b? And I think we can think about it for a little bit and realize that question mark has to be a 1. Okay, now we're going to evaluate, and we're going to do the same thing, except it's not set up that way. So you have to think about this as saying, what does this equal? And we're going to do this without a calculator as much as possible. So 3 to what mystery power is going to come out to an 81. Now I provided you with a list of perfect squares, cubes, fourths, fifths, so you can refer to that, or if you don't know this off the top of your head, you could start typing things in your calculator to see what will work, but turns out that that question mark is going to have to be a 4, so the answer to this problem is 4. Same thing here on number 9. 5 raised to what power is going to give us a 0.04. Now, just so you know, a 0.04 is 4 1/100ths, which is the same thing as a 1/25th. So if you think about this, 5 raised to what power has to give us a 1/25th. It's going to have to be a negative exponent because it's going to have to take the 5 and flip it to the denominator. And the way I'm going to make a 5 change to a 25 is to square it. So I think that this exponent is going to have to be a -2. And if you don't believe me, try it on your calculator. Take 5 to the -2 and see if it comes out to a 0.04. And it does. Okay, number 10, 1/2 raised to what power would give you an 8. So similarly, we need to take the 1/2 and flip it back to a whole number, so I know the exponent's going to be something negative. And then 2, changing it to an 8, what power would I need? Well, that would be 2 to the 3rd power. And again, you could go back to your calculator and make sure that this works, but it does. And then on number 11, 9 raised to what power would give me a 3? Now this is kind of unique because we have to think about how to break down a number to something smaller while still raising it to an exponent. And the relationship that I see between a 9 and a 3 is that if I took the square root of 9, that would equal the number 3. So I got to think about what exponent represents a square root. And that exponent I'm looking for is 1/2. So the answer here is 1/2. And the answer here was -3. Now, do you have to set it up every single time this way with a question mark? No, as you get really good at these, you're going to be able to just look at them and tell me the answer. Okay, now 2 types of logarithms we can actually do on our calculator. I'm going to pull up my calculator. Where is he? There he is. So, turn them on. You're going to notice 2 logarithm buttons, and they're over here on the left. This is called the common logarithm, and he's a base 10 logarithm. And this is called a natural logarithm, and he's a base e logarithm, the number e. Now, I don't really know why it's ln. I think it has something to do with some other language and the derivation of how they came up with natural logarithms. My guess is that it's something French. I don't know why. I just remember that in some history book. But these are the 2 types of logarithms that we could easily compute something on our calculator. So if we were to be given a question like number 12 where it says, what's the common logarithm of 5? That's as simple as just saying log and then typing a 5. And the answer is something gross, 0.699. So go ahead and write that down. Whoops, that one right there. And then common logarithm of 21. Again, you want to pull up your calculator, because these are, if I give you something like this, it's probably because you can't do it easily in your head. Since this is a base 10, there's no way to go 10 to what power would give me a 21 easily. So that's a 0.13, I think it was a 1. Nope, 2. Okay, and then the natural logarithm is just the other button. So natural log of 0.1 and natural log of 2. Let's go ahead and type those in. Natural log of 0.1 and then natural log of 2. Now notice I didn't close my parentheses after the numbers. That's just because there's nothing that followed the number. If I was doing more operations, multiplying it by something, adding it to something, I would have to make sure to close the parenthesis to stop the logarithm. So negative 2.30 and 0.693. Okay, so those would be very easy questions if I gave you those on your homework, and I think there are a few. But you will need a calculator. Science connection. The slope S of a beach is related to the average diameter d. So slope is S, the diameter d of the sand particles, and it's given to you by this equation. So we're talking about beach erosion, which we don't live on a beach, but if you did, this would be a very important concept because you don't want your beach to be washing away. So depending on the size of how big the sand particles are, that's going to affect how easily the beach will erode. So the question is, find the slope of a beach if the average diameter of a sand particle is 0.25 millimeters. Now this was a diameter is 0.25, so when I look at my equation, I just have to identify which variable am I supposed to substitute the 0.25 in. And since it's diameter, I'm thinking I put it in for the d. So we have 0.149 plus 0.118, and then it's going to be times the logarithm of the diameter, which is 0.25. Now notice this was a common logarithm, which is good news. That means it's something I can do on my calculator. So I'm going to grab the calculator and just type very carefully 0.149 plus 0.118 times the common log of 0.25. And it's roughly 0.08. Now, again, I don't live on a beach, so I don't really know what this means, but I imagine if you are like a hotel beachfront property, they have some standards, and if the slope of your beach is too steep, it's possible that they'd have to close the beach down. Now we're going to use something called an inverse property of logarithms to simplify, and these are actually pretty easy. I'm going to write a couple generic properties down for you. First one says log base b of b to the x power. So if you notice that the base of the logarithm and the number that follows are the same number, what happens is they end up canceling out and just dropping down the exponent, and it comes out to an x. Now similarly, if you have an exponential base raised to the log, oops, I don't want to use a 5, If you have an exponential base raised to a logarithm of that same base, they too are going to just cancel out, and it's going to drop down the x, and that's all you have left. So when I look at number 17, this is going to be property number 1, this is property number 2. When I look at number 17, this looks like property number 1 where the bases match. So all I have to realize is log base 6 of 6 are going to cancel, and this comes out to the number 3. Number 18 looks to me like it's property number 2. 5 to the log base 5 cancels, leaving you with just a 13. Now, natural log, remember, he had a special kind of base. Even though he was a funny looking logarithm button on our calculator, he was a base e. So remember, natural log are base e. So e and natural log are still going to cancel out, leaving you with a 15. A little strange here on number 20, there's a 2 in front. You don't know this yet, we're about to learn it actually, but when you have a number in front of a logarithm, he actually can go back up into the exponent. So this is really e to the natural log of, instead of 3 squared, I'm going to write that as 9. And then again, we can see that e and natural log cancel. So your answer here is going to be a 9. Okay, 21. You could put this 5 back up in the exponent, or you could just leave it out in front. So it's totally up to you. So I'm going to do this problem 2 ways just to show you. You could put the 5 back up here and make that natural log of e, and then when you put an exponent back up and you have exponent to another exponent, you multiply those together, so that would be a 15. So this would come out, remember, natural log and e cancel to a 15. Or if you just wanted to leave the 5 in front and realize that natural log and e are going to cancel, this is just going to become a 5 times 3, which again equals 15. So you can do this problem 2 ways. Okay, number 22. Remember, common logarithms, when there's no base written down, we assume that's a base 10. A common logarithm. So 10 to the log base 10 would cancel, giving you a 2. And then here, this is kind of a strange question. The 3 and the 9 don't match. So we have to think of a way, if we want to use a property like this, to rewrite the 9 so that he is a 3. So I'm thinking, what if we wrote 9 as a 3 squared? And then we used a couple exponent properties. So when you have a power to a power, remember we're supposed to multiply those together. So this is really log base 3 of 3 to the 2x. And now that the base and the number here match, we can say log base 3 of 3 cancel, leaving us with just 2x. There's a couple questions on your homework like that where you, since the base and the number aren't exactly the same, you have to do a little work to rewrite them so they are the same. Okay, we're going to now find inverses. So remember, when we found inverses back in chapter 7, back in unit 3 actually, we first switch our x and y, and then we had to rewrite it so y was solved for. So first, number 24, we're going to rewrite this as x equals log base 3 of y. Now in a little, let's see, next lesson actually, we're going to learn how to solve this through other methods, but for now, what I want you to do is think about how you can rewrite logarithms. Remember, we had log base b of n equals a, and we could rewrite this into exponential format, which was base to the answer equals the number. So let's use that technique here in this next problem. So we're going to take our base, which is 3, raise it to the answer, which this time is over here, to the x, equals that leftover number y. I think we're done. So if you like to rewrite it so the y is first, that's fine. But your answer is y equals 3 to the x power. Now notice the original was a logarithmic equation and the inverse is an exponential equation. And that should always happen because those are inverses of each other. So here we're going to rewrite x equals log. Now there's no base written, and I'd like to have one. And remember, common logarithms, when there's no base provided, we assume it's a 10. And then switch that for a y. So now again, we use this translation formula to go to an exponential form. So base to the answer equals that leftover number. And we have y by itself. I'm just going to flip it around so it's in the right form. you should be noticing some similarities. When it was a base 3 logarithm, it turned out to be y equals 3 to the x. When it was a base 10 logarithm, it was y equals 10 to the x. Now 26 is a little more complicated, but he is a base e, because he's a natural log. So first thing I'm going to do is rewrite it. X equals natural log. I'm going to put a little e down here just so I remember. And then instead of x plus 1, remember it's y plus 1. So our next step is to translate it into exponential form. So I'm going to say e to the x power equals the leftover number, which in this case is y plus 1. Now remember, we always want to get y by itself. So if you want to get y by itself, the last thing you have to do is subtract the 1 over. So my final answer, if I flip it around, y equals e to the x power and then minus 1. Again, we always think of inverse as opposites. So earlier in the original we added 1, in the inverse we subtract 1, and that shouldn't really surprise us. Okay, when we are graphing logarithms, you're going to notice that your calculator can help you a little bit, but your calculator does a really cruddy job of graphing it. And you don't know that until I tell you that. So go ahead and grab your calculator, and since it's a common logarithm, we can go ahead and type this guy on our calculator. So common logarithm of x. You can close the parenthesis for good habit, but you don't have to in this case. Now hit graph, and if you have a standard window, your graph looks like this. So kind of resembles a square root graph at first, and your calculator doesn't do a real good job of showing you that there's a vertical asymptote right here. Hit the trace button, and notice he's not showing you much of anything right now on the trace because it says x equals 0. Well, there's an asymptote at 0, so there actually is no value when you get to 0. But if you go a little bit to the right, hit the right arrow, you're going to notice that your calculator starts going along the curve. Now because of the scale we have, it seems to just kind of stop, but actually what happens is this graph goes down forever along the y-axis. So I'm going to do my best to graph this, but I'm going to go to my table first to pull up a couple points. So 1, 0, 2.3, 1, 0, 2.3, and it just kind of goes up slowly from there. Now, because I know what this looks like, woo, that's ugly. You do a better job of graphing than I just did. That's what I mean by a vertical asymptote. This end over here comes down along the y-axis. It'll get really, really close to 0. It'll keep getting closer and closer and closer, but it's so minuscule that your calculator can't even pick up on it with the pixels. So the vertical asymptote in this particular graph is at the vertical line, so it's x equals 0. The x-intercept on a common logarithm is always at the point 1, 0, unless it's been transformed. The transformation equation for a logarithm is very similar to the transformation equation that we have always seen. So it's x minus h and then plus k. So the h would be a horizontal shift, right or left, and the k would be a vertical shift. The domain on this particular graph goes from 0 to infinity, and notice there's a parenthesis on 0 because it doesn't actually get to 0, so there's no bracket. And then the range goes down forever and then up forever, very slowly, but up forever. So negative infinity to infinity. This is kind of opposite of what we saw in our growth and decay functions, and that's because they are inverses of each other. So when I look at number 28, if I tried typing that on my calculator, x plus 1, you might notice that it's been shifted left, and hopefully that makes sense to you because when there's an x plus 1 inside the parentheses, it's been shifted left. So grab some points off your table and plot them. Now I'm going to do the best I can to graph this, but instead of having a vertical asymptote at 0, we now have a vertical asymptote at negative 1 because everything's been shifted left 1. So that x-intercept that used to be at the point 1, 0, now it's been shifted left 1, so now it's at 0, 0. And again, your calculator will not show you the vertical asymptote. You have to know that it is there. So we do notice that this has been shifted left 1 unit. So the domain now, instead of being from 0 to infinity, it's now from negative 1 to infinity. The range is still negative infinity to infinity. That never changes. The vertical asymptote is now at the line x equals negative 1, and the x-intercept is now at the point 0, 0. And I think that is close to the end of our lesson. Okay, log of x plus 4. This time, if I graph this on my calculator, you're going to notice that it had a shift of up 4. And maybe you didn't notice, and that's okay. So that vertical asymptote at 0 is still there. I like to draw in a little vertical line here, so I remember not to cross it. Normal logarithm graphs have a y or x-intercept at 1, but since it's been shifted up 4, I'm going to place him up here. And then you're going to grab table points off of your table, but since I'm not going to be able to graph that accurately, whoa, I'm not going to bother. Oh, jeez. Okay, pretend. Now, since it wasn't shifted right or left any, it still has a vertical asymptote at 0. So the domain is still 0 to infinity. The range is always negative infinity to infinity. The vertical asymptote, in this case, is still at x equals 0. And the x-intercept, I'm going to have to get off my calculator because I don't know what that is. Whoops. And remember, x-intercept would be where your y value is a 0. Now you're not going to be able to tell that off of your table. So go to your graph, and we're going to find our x-intercept using our trace function menu. So remember, we go to number 2, which is the 0 finder, and they want you to go a little bit to the left, which might be a little hard. I'm going to go this way. You know what I'm going to have to do? Forget this. We're going to go to the home screen. No, we're not. I'm going to get a better window. Go to Window. I want my x's to go from 0 to 1. This is kind of strange. And instead of counting by 1s, because that wouldn't be very exciting, I'm going to have it count by 0.2s. Now for my y's, I don't really have to go negative 10 to 10 because I just want to see where it crosses the axis. So I can just go negative 1 to 1. I won't give you anything this tricky. And then hit graph. And hopefully we're going to be able to see it. Okay, or not. Alright. Well, with the techniques that you guys currently possess, we're not going to be able to find the x-intercept with our calculator because it thinks the graph ends because of the pixels. So don't worry about finding the x-intercept on this graph. It's possible I've already changed the notes so you don't have to worry about finding the x-intercept. We're going to find algebraic methods for finding the x-intercept soon, but for now, just don't worry about it. If you were really worried about finding the x-intercept and you really wanted to figure it out, what you could do is you could start trying to figure out values that you could plug in for x that would give you a 0 for the y. So if you took like the common log, and I'm just going to make up this number, I don't really know, of 0.002, and then I added 4 because that's what the function says. You'd see I'm not quite to 0 yet, so I have to go even smaller. So I'd have to go common log of 0.00002. Again, I'm just making these numbers up, I don't really know, and then add 4. Oh, too far. See, now I'm negative. So how about common log of 0.0002, close parenthesis, plus 4. So kind of somewhere in between there. So log of 0.000, how about 1? Plus 4. There we go. Calculator says you did it. So the x-intercept apparently is at 0.0001. Alright, that is a nasty problem, sorry. So again here, domain and range are going to be affected because we're going to be translated. So this guy was shifted right 2 units because of the -2, but then down 3. So you can pull things off your calculator, but what I'm going to think about first is my vertical asymptote. If he was normally at 0 and then shifted right 2 units, he's now at x equals 2. And remember, the vertical shifts don't affect a vertical asymptote. Now down 3, all that's going to affect is where my x-intercept used to be. So remember, on a normal logarithm graph, the x-intercept was at 1. But if I shift right 2 units and then down 3 units, at least I've got a nice point to plot. And then of course, oh geez, you're going to do a much better job than I'm about to do than what I just showed you. But the domain, we can answer pretty easily, even off of my credit graph. It goes from 2 to infinity. The range is always negative infinity to infinity. The vertical asymptote is now at x equals 2. And then the x-intercept, I think we're going to be able to find on our calculator pretty easily. So let's go ahead and type in x minus 2, oops, not plus, minus 2, and then a minus 3. And then hopefully, oh yeah, I have a silly window. So go to zoom 6, back to my normal window. Oh geez, the x-intercept's going to be way off in no man's land, way far. So I'm going to go to like 50 and see if I can see it. Now instead of counting by ones, I'm going to count by fives just so it doesn't take me forever. Okay. Oh, not far enough. I guess I got to go way farther than 50. Let's try 200. And now let's count by tens so that way it doesn't take forever. Still not far enough. Alright, let's go to 500. And this time let's count by 50s. Okay, graph. Oh my goodness. Can't really tell if it crosses. So I'm going to go big. I'm going to go to 1,000. And I'm going to count by 100s. Now, quite certain it crosses somewhere in here. So let's find our x-intercept using the 0 finder. I can tell from the coordinates that it's below the y-axis, so I'm going to hit enter. And then I'm going to watch my coordinates as I scroll. Uh-oh. I didn't go far enough on my window. 2,000. Again, I won't give anything this nasty. Okay, I am certain it crosses the x-axis now. So now we're going to go find the 0 by going, okay, we're already a little bit to the left, that's good. A little bit to the right, good. And it's at 1,002. So I had a really good estimate when I picked 1,000, I just wasn't quite far enough. So our x-intercept, yikes, is 1,002. Alright, that concludes our lesson. And sorry about all the mess ups on my graphs. The next lesson is about properties of logarithms, and I think you're going to like that one a lot.